This is a Sencore model FE16 FET voltmeter, and the date that this was made is at least into the 60s. I have a schematic that shows a date of 1968, so this thing goes back quite a few years. And unlike the old vacuum tube voltmeters, this one uses field effect transistors. It uses two of them in a balanced bridge configuration that replaces what used to be done with an old dual triode vacuum tube. And the nice thing about that is there's no tubes to heat, very low power consumption, and these could actually be battery driven, which was convenient for service technicians that had to be out in the field. This particular one used a 9-volt transistor battery and then I believe it's a C-cell 1.5 volt battery. These were nice meters. In fact, on DC they have an input impedance of 15 megohms and on AC 10 megohms, so they were quite accurate. And you might ask yourself, well, why would you want an old meter like this anyway? Well, this has some really unique features in it that are pretty valuable, and to me, one of those is the zero adjust knob. I can set this to 0 and then read plus and minus voltages on the scales here. I'm not going to use this to measure resistance because a digital voltmeter is a lot better for that. Although they are nice if you wanted to test a potentiometer. It's a lot easier to watch a moving needle than watch digits on a digital voltmeter. I want to use this on a bench, so I don't care about battery power. So what I want to do is I'm going to replace the 9-volt battery with a 9-volt supply from a wall wart. So that's going to be the extent of this video. This should be a fairly easy project to do. If you look on the unit here on the back, it has a door that is removable that has a battery compartment that holds a 9-volt transistor and a C-cell battery here. Here you can see the back of the meter. So what I plan on doing is I'm going to add a barrel connector chassis jack onto this that I can plug in an external DC supply. Looking at the schematic, there isn't a common ground between the 9-volt transistor and the C-cell. So using a single supply wouldn't work here. And like I say, I don't really care about the resistance range anyway, so this should be able to be powered by the 9-volt transistor battery because the 1.5 volt C-cell is only used for resistance measurements. What I plan to do is mount a chassis mount barrel connector similar to this one. There's a lot of different styles that I can plug in a barrel connector from a wall wart and make the contact. So that's the plan. And here's a quick tip here. Pizza boxes make wonderful component storage boxes. Here's barrel connectors. And the nice thing about them is you can stack them. You can put them right on top of each other. Right on the outside what's in it, you can stack these things up. Really makes storage, which can be a real problem with parts anyway. Quick tip. And the guy was nice enough to sell me a bunch of these boxes. So they don't smell like pizza. They smell like electronics. I've taken the back off the unit here, and I just discovered this is going to be a repair before modification, it looks like. If you look close here, there's 3 resistors that are burnt. R9, 10, and 11. And those 3 resistors are right here. 9, 10, and 11. Looking on the schematic here, you'll notice our 9, 10, and 11 are used in the R times 1, times 10, and times 100 range of the ohm meter. And these are these are burnt quite badly here, so they let out the manufacturer installed smoke. I don't know how they got all three of them, unless they switched through the ranges. Now on the times 10K range, it appears they use R4, which is this resistor right here, 66.7K. These all look like they're 1% or better resistors. In the R times 1 megohm range, following back through from the negative lead here up through the switch, here's the bottom here, here's the bottom here, so these two are connected, and that would connect directly up here through this 5 megohm resistor in series with a probe. So I need to see if this resistor is burned or not. I have to see if this is 5 meg. So what I'm going to do, R1, which is 5 megohms, 1%. That would be this resistor here. And that measures 5.08. So that resistor is good. R1 is good. I want to look at R4 and see if that's good here. That's a 66.7K resistor. 66.76. So that resistor is good. So it looks like the only resistors burnt up whenever this happened was these three here. So 9, 10, and 11. Since I won't be using this in the ohms function, I guess that won't make any difference. But what I need to check out is make sure I don't have any burned contacts or other components here. So I'm going to do a quick inspection of that, and then I'm going to connect 9 volts up and see if the meter will operate on just 9 volts. And the 9 volt battery is connected here, and that's just to run the two FETs here. Here's your two TR1 and TR2 are your two FETs. I have a 9 volt power supply connected to the 9 volt battery connector on the meter, and I have a DVM connected to the input of the meter, and I have an external power supply connected here to both meters in parallel. So what I'm going to do, I'm going to turn it on. I'm going to see now if I can zero the meter here. Should be able to. Right now I'm just looking to see if it's close. Now I'm going to go through the scales and see if it varies much. And it's not, which is good. There's the 1000 volt range. You can still zero it. So I'm going to put it on the 10 volt range. Zero it fairly close there. I'm going to connect an input. I'm going to slowly bring up the voltage here. And you can see as the needle goes up, okay, I'm on the 10 volt range, which would be here. So let's set it at 5 volts right in the center. Right about there. 4.98, so that's pretty close. Let's go to the 30 volt scale. And we'll run it up a little higher here. That would be this scale here, this would be 30. So let's go to 15 volts, which would be here. We're reading 14.6, pretty close. Let's go up to the 100 volt scale. Now this supply only goes up to 50, so we should be able to take it up close. $50 volts would be here. We got 50.92. So apparently this is working on DC, which is really all I'm interested in here. I think I'm going to go ahead with my modification to power this thing externally. So I'll do that next. This case is surprisingly heavy sheet metal here. I don't know what the gauge is, but it's pretty heavy. What I'm going to do is mount this jack here on the dot here I put. That should keep me away from any components on the boards here, and also a convenient spot to plug in a barrel connector and power the unit. So that'll be the next step. Here's the barrel connector mounted on the back of the unit here. So I can just plug in a outside connector and power the unit. So all I have to do now is connect the positive and negative leads here to this jack and put it back together and check the calibration, and we should be good to go. Here's the power jack mounted, the barrel connector. I put a Schottky diode in series with a positive lead just in case someone connects reverse polarity in here. We don't want to burn up any more components here or let the manufacturer install smoke out. Anyway, that's the detail of the power jack. I decided to add an addition to this project, and that is to add an internal voltage regulator. A lot of these wall warts aren't the most stable output voltages around, so what I'm going to do is add a 3-terminal regulator. I got a couple of them here. I'm going to try a 7810. It's a 10-volt regulator, and it'll be a simple circuit. I'll build it on a small piece of perf board. You can get these things. I buy these whole bunch of these. They're handy to have. Just break off a section of it, and I can mount these parts on there. And then this little board should mount right in here fairly easily. I can probably use some double-sided tape. And that way, if I want, I can use, for instance, I can use a 12-volt wall wart, which is pretty common. This needs 9 volts to replace the 9-volt battery here. So, and if this is a little high, I'll just put a diode, a silicon diode, in series with the output to drop it another 600 millivolts or whatever. Keep it in the range. That way when I test it and do the battery check, I'll make sure it lands in the middle of the green area. So I'm going to build that circuit next, and then we'll see how it works. Stand by for that. Here's the final circuit. Right now I'm running on the input here. This is just a standard 3-terminal regulator. There's 12.3 volts in and 9.9 volts out. So I need about a 2-volt headroom here for this to work. So a 12-volt wall wart will work, and if I want to, I can go up even more. So here's the input. I'm going to run it up to, let's say, because some of these wall warts are kind of high, and this doesn't use a lot of current. Let's run it up to about 16 volts. And our output is still 9.9, so this should be good for any input voltage above 12 volts or higher. These have an upper limit of 30-some volts, but I won't have to worry about that, and this will not get hot enough where you need a heat sink. So now I'm going to mount this on that back plate, and then we'll give it a shot. So stand by. I have the unit powered up through this external jack that I just installed, running in 9 volts. So let's turn it on. Turn on battery, and it's in the green. On the lower scale here you see a green. It says battery good. If the needle falls within that region, the battery's fine, which in this case we don't have to worry. So let's put it on DC positive, and I'm going to 0 it. I like the mirrored scale too, which I don't know if you can see here. Gets rid of the parallax. Here's one of the nice things about these meters, that you can adjust the zero center with a zero adjust knob here. If you set it on 0 and you're going to measure a device that's either increasing or decreasing, for instance, you're tuning a FM discriminator or something like that, but anyway, I have it on 0 centered. I have a pot here that I'm going to adjust. So this is my adjustment, and I want to look for a trend, either plus or minus. So as I turn this and adjust it, let's say I'm tuning for 0 here. Now with a digital meter, the numbers are going to be jumping all over the place, but you can see here I can adjust it right on 0. So that's one of the things nice about an analog meter. So you should have at least one of them. And these are really cheap. You can get them at Hamfest. This was, I think, like a couple, $5, something like that. And I didn't fix the ohm meter ranges because I really don't care about those, because I'll be using a DVM for those. But now that I can run this off of a line operated supply, I can put it on my bench and just flip it on when I need it. And all I did was put a jack on the back of this. And like I say, I did put a Schottky diode in series with a hot lead here, the positive lead, in case someone connects polarity and backwards. They're not going to burn up anything. So this actually is a pretty nice meter, very sturdy. I was lucky to obtain a schematic for this meter, and so I identified, here's the 3 resistors that were burned up. That was the only components I found that were in bad shape. This is an interesting circuit. It's the way it's drawn, it isn't quite as intuitive to see how it works, but you know, this is basically your standard balance circuit here with a meter in the center. In the old days, these FETs would be replaced with 2 triode vacuum tubes. Usually they'd use a 2-section tube, and when the 2 were balanced, the meter would read 0. Now these 2 FETs form a differential pair here, and here you can see the meter in the middle is connected through the sources here. They're fed a common voltage here to the drains. So anyway, when you balance this out, once you connect an external voltage, for example, that will change the gain of this stage here, and that will unbalance the differential pair, and then you'll get a meter indication on the meter. And then by switching in various multipliers here, you can get different ranges. Or in the case of the ohm meter, they had these 3 resistors, this 5 meg, and this 66.7K resistor that were used in the ohm meter region here. And of course you've got your calibration pots in here that are internal adjustments. Here's the 9-volt battery, the original 9-volt transistor battery, which I replaced. And then over here you see where they had the 1.5 volt C cell that was used in the resistance measurement. Fairly simple circuit. Not too much that could go wrong with these things. These are very well built. I always like the old Sencore equipment. They seem to be, you know, built to take a rugged use here. Anyway, that's just, if you're interested, here's a schematic of the FE16 made by Sencore. That'll do it for this one. I hope you enjoyed it. Thanks for watching, and we'll see you in the next one. Bye for now.